Deep Time Chapter 9. When I talk about geology, I compare it a lot to crime scene investigation. That is because the layers, how they're laid down, the rock type, and the shape of the sediment grains, these all give us clues to the formation of those layers. And we're also going to be putting things in order: what came first, second, third, and so on. And we're going to also be applying a lot of concepts we've learned over the whole semester. If you've ever been to the Grand Canyon, you'll notice that there are a lot of layers. Those layers are very thick, and that took a very long time for those to be deposited. So there's some of Earth history that's recorded in the Grand Canyon. And John Wesley Powell, he was tasked with mapping the Grand Canyon. He was a geologist, and Lake Powell is named after him, and he was a former military. Now, when we talk about deep time and geologic time, we need to talk about relative age. Relative age is how old one layer is with respect to another layer. And this is putting things in sequence: what came first, second, third, and fourth. And we'll talk about the different rules that are used to order those layers. And then numerical age. Numerical age is an absolute age date. So when somebody says that a rock is 113 million years old, that was determined by radioactivity. And we'll talk about how they're able to determine age from radioactivity and radioactive minerals. Now, this is an image of John Wesley Powell on the Colorado and Green Rivers, and he was tasked with mapping and surveying the Green River and the Colorado River. Now, one of the interesting things about John Wesley Powell is he actually did all this and hiked and surveyed the Grand Canyon, and he just did it with one arm. Now, some of the different observations he did in the Grand Canyon were he saw that there was a lot of thick layers of rock. He did mapping and surveying of different elevations of those layers. He looked at erosion and deposition. Now, these are processes that occur today, but they occur very slowly. And all of these different observations pointed to suggest that the Earth must be very old. Let's discuss uniformitarianism. And that is a word salad, so even geologists shorten it to the principle of uniformity. This is where the physical processes operating in the modern world also operated in the past. So the key tenet to the principle of uniformity is the present is the key to the past. The present is the key to the past. So what we observe today happened in the same manner and at the same rate in geologic past. Now, one of the proponents of the principle of uniformity was a man named James Hutton, and he lived from 1726 to 1797, and he is considered the father of modern geology. This is basically where you use modern analogs to make interpretations about geologic past. Now, this is an image of mud cracks, and mud cracks form when wet clay, okay, so that's really fine-grained material, dries out, it starts shrinking inward, and it starts to curl up on the edges, and it forms a polygon shape, okay? So we can apply the same principles we see today to what we see in the past. So if we see a really fine-grained mud-sized particle that has a polygon shape, we can infer that basically these particular rocks were subjected to the same conditions that we see today, a wet, dry action. Now we're going to discuss relative age dating. Now, relative age is the age of one feature with respect to another. So this is putting things in sequence of events. What came first, second, third, fourth, fifth, and so on. Now, these are the different principles or rules used to determine relative age, and these were developed by Nicholas Steno. The first is the principle of original horizontality, the law or the principle of superposition, the principle of cross-cutting relations, the principle of bake contacts, and the principle of inclusions. And we'll get into each of these in a moment. The first is the principle of original horizontality. This basically states that the layers of sediment when first deposited are roughly horizontal. So as sediment gets laid out, it gets deposited in a roughly horizontal fashion. And a good example of this is this tidal flat in France. And we talked about this during our ocean section where we have our flood tide and our ebb tide. And in between, there is a period of slack water where these fine grained mud sized particles settle out and get deposited. And as you'll see, these layers are deposited roughly horizontal in their original orientation. So what that can tell you is that anytime you find it in some other fashion besides horizontal, something else has happened after deposition, okay? So that starts telling you what order things have happened. So here we see these different layers, okay? Now, this is just showing us what an earth scientist sees. Now, these are different sandstone beds, okay? And we see sand being deposited in either beach or desert environments. And this has some cross bedding. This would have been associated with dunes. You can have dunes at beaches or in desert environments. And so these layers are deposited roughly horizontal. So we know that they're in their original orientation. The next is the law of superposition. This tells us that each layer of sedimentary rock must be younger than the one below it. Basically, this is stating that the oldest rocks are on the bottom, okay? Now, these are some superposition diagrams. Now, at time 1, we have a sand layer that gets deposited. At time 2, we have a second layer that gets deposited. And at time 3, we have a third sand layer that gets deposited. Now, based on the principle of superposition, we know that the oldest layers are deposited on the bottom, which makes sense, right? And the youngest layers are deposited on the top. So that tells us the order in which things are laid down, okay? So another good analogy to think about is a laundry basket. Now, at the start of your week, you have an empty laundry basket. And as each day ends, you put your dirty laundry into the basket. So on the first day, your oldest, dirtiest layer is put on the bottom. On the second day, you have a slightly newer dirty laundry that you put on top. On the third day, you have slightly younger laundry that you put on top. And on the fourth day, you have your youngest, dirtiest laundry on the top, okay? So basically, as you move upward, you basically have younger and younger deposits. They're from more recent times. Now, according to these principles, which layer is the oldest? Okay, so these are all roughly horizontal, which helps us. Okay, according to the principle of superposition, the oldest is on bottom. Okay, so this would be our oldest layer, and as we go up, we have younger and younger layers. It looks like an altering between limestone layers and shales. So as it goes upward, we have younger and younger rocks. The next is the principle of cross-cutting relations. Now, this is if you have one geologic feature that cuts across another, the feature that has been cut is older, okay? Now, a good way to think about that is a birthday cake, okay? Now, can you cut a cake that doesn't exist? No. So how do you make a cake? You mix the ingredients, you put it in the oven, you bake it, you let it cool, you frost it, then you cut it. So that tells you the sequence, which came first, which came second, which came third. If you have anything cross-cutting anything else, you know that those layers had to be there first, otherwise they couldn't be cut by it, okay? So the principle of cross-cutting relations tells you that whatever's being cut is older and whatever is cutting it is younger, okay? So this is an image of a dike, and remember a dike is discordant, and so it cross-cuts the sedimentary layers, and it is tabular or sheet-like, okay? So what is the age of this dike compared to the sedimentary layers? It's younger, okay? So let's go over each of these layers. We have this tan layer that gets deposited, we get this gray layer that gets deposited, then this kind of tan sandstone layer that gets deposited. Then we have a dike that cross-cuts it. Now, after the dike, there was another layer, this kind of red sandstone that was deposited after that, okay? So this tells us that order of events. The next principle is a principle of baked contacts. Now, this is where you have the igneous intrusion that bakes or metamorphoses wall rock so that the rock that has been baked must be older than the intrusion. Now, can you metamorphose a rock layer that doesn't exist already? No. By definition, metamorphic rocks come from pre-existing rocks. So you cannot metamorphose a rock that didn't already exist. So here's a good illustration. We have these different layers, and how do you tell what order they came in? What was the sequence of events? Okay, so we have this pluton here, and it's cross-cutting all these different layers, and then it's metamorphosing those layers. So that tells us metamorphism can't happen without existing layers, okay? So here we see this layer was deposited, it's the oldest, it's on bottom. Then we have our gray layer being deposited. Then we have our tan sandstone. After that, the pluton intruded. This looks like either a stalk or a batholith intruded. And the surrounding rocks were baked or metamorphosed. So that occurred last, okay? The next is the principle of inclusions. This is where a rock containing an inclusion or fragments of another rock must be younger than the inclusion. Okay, so think about that for a second. Rocks containing an inclusion, basically an inclusion is a fragment of another rock, must be younger than the inclusion. All right, so here we have our different layers. The tan layer came first, then there's our gray layer here, and then there's this tan sandstone here. Now, it looks like there was a sill that intruded. That gives us a clue first because you cannot cross-cut something that doesn't exist. So there's a sill that intruded, and there's chunks of the sandstone in the sill. So we know that those inclusions or chunks must be older than the sill because you can't include a chunk of something unless a chunk already existed. What came first, the raisin or the raisin bread? Raisin or the raisin bread? The raisins. They are like the inclusions. So they would have been there first, so they would be older, okay? And then our raisin bread. That is like your surrounding rock. So those have to be younger. So how do we make our raisin bread? You buy the raisins, you basically make a bread, you let it rise, and once it rises, you put it in the oven to bake, and then you have raisin bread. Now we're going to talk about unconformities. An unconformity is a gap in the geologic record, and this represents a hiatus. This is a period of time not represented by strata, okay, or layers. So this can be either during periods of non-deposition, okay, or during periods of erosion where that material has been removed away. There are three different types of unconformities. The first is an angular unconformity. This is where rocks below are tilted at an angle to the younger overlying rock, such as at Sakar Point, which we'll talk about in a minute. How an unconformity forms is basically you have your sedimentary layers. They are laid down horizontally, and then there's some type of tectonic activity that causes folding to occur. And as that folding occurs, you get very tilted or folded layers. Now, whenever you have tectonic activity, often this produces high points, and as those high points occur, you get mass wasting, erosion, weathering, and that moves a lot of sediment downslope. And that's basically erosion. And so that material gets eroded away. And so here we see that material that's been eroded away and then layers being deposited on top of it. So with our angular unconformity, layers underneath the erosion surface are at an angle. And a good example of this would be Sakar Point in Scotland. This is an angular unconformity that formed due to tectonic activity. There was layers that were folded and then material was removed away. And so this represents a gap in the geologic record. The second type is a nonconformity, and a nonconformity is when younger sedimentary rocks overlie older igneous or metamorphic rocks. And we talked about igneous rocks and metamorphic rocks, where those form and what type of environments. So those typically don't form at the Earth's surface, okay? So we'll talk about that in a minute. So here we have some granite that has intruded into the surrounding rock layers, okay? So it's cross-cut it essentially, okay? And we know that granite, it's coarse-grained and it's felsic, so it forms very deep within the earth. That coarse grain indicates that it cooled very slowly deep within the earth, okay? So when we see, for example, granite at the Earth's surface, we know that there is a gap in the geologic record because that doesn't make sense geologically. And so what we have here is with time, there's erosion that removes all of those overlying layers. And then with time, we get more deposition of sedimentary layers on top of that. The next is a disconformity, and this is the hardest one to identify in the field. This is where beds above and below the unconformity are parallel to each other. Sometimes they're even the same rock type, and so it's hard to see the gap. But the contact between them represents a hiatus, so either a period of non-deposition or erosion. Now, here are some sedimentary layers that are being deposited, and they start eventually being eroded away. And as they get eroded away, new layers get deposited on top of them. And this is a disconformity. So it's a gap in the geologic record because some of that material was removed away. Now we're going to talk about what are called stratigraphic formations. And we've used this term frequently this semester. Strata are the different layers. Okay, so these are sequences of rock layers that can be traced over a fairly broad region. And a contact is the boundary between two formations. And when you have transitions in the rock types, these often represent changes in the environment they were deposited in. And we have what is called the stratigraphic column. This is basically a chart that represents the order of formations and their relative thickness. So this is a stratigraphic column of the Grand Canyon. And on the left, we have a image of the Grand Canyon. And here we have the different rock layers and their relative thicknesses of the Grand Canyon. And you could pick out different features, like, for example, here is an angular unconformity and a non-conformity where we have this Vishnu schist, and then over that metamorphic rock. And then over here we have these rocks at an angle, which forms an angular unconformity. So what geologists do is we unravel geologic history. So we come across rock formations like this, and we make interpretations, and we basically work our way backwards, okay? So when we look at this, we use those different relative age rules to basically see what happened first, second, third, and put them into sequence. So what happened first is we have this sequence of strata that was accumulating or being deposited. Then we had intrusion of the sill. And then we start seeing folding and uplift and erosion take place. Okay, so this starts folding, and then we see a magma body, a granite pluton intruding. Okay, and these often occur at the core of mountains, so during mountain building events. So these often happen very closely near folding. Then we had a fault that occurred that's an offset of those layers. Okay, and that fault cuts across that strata and the pluton. And then the dike intrudes across the layers, and then we get erosion that forms a present land surface. So a geologist takes these complicated histories and using those different rules is able to reconstruct what order those events occurred in. Now, this is an outcrop of some different stratigraphic columns. Not all of geologic history is going to be found at one outcrop, and there is geologic history recorded in these rocks. We have to do what is called correlation. Now, correlation is basically matching rock units over a large area. And this goes to the principle, what we call the principle of lateral continuity. That is basically as rock layers are deposited in continuous layers, they get deposited over a really large geographical area. So for example, the Grand Canyon here, the layers at the very top, like the Kabyle limestone, the Moenkopi formation, they correlate with Zion Canyon and the Painted Desert. Now at the top of Zion Canyon, we have the Navajo sandstone and the Carmel formation. We can correlate that with Bryce Canyon, okay? So that gives us a more complete history. Remember we talked about superposition? We know that the oldest layers are on bottom. So as we go up into Zion Canyon and Bryce Canyon, we know that we are getting younger and younger layers. And so we get a more complete history when we could correlate across different outcrops. And we can use that using the principle of lateral continuity. As they get laid down, they get deposited over these very large areas. And here is just the Grand Canyons, basically that river those rivers that are carving into that landscape. Another thing we're going to look into is called paleontology. Now, we've used this root before. Now, what does paleo mean? It just means ancient or old, okay? So paleontology is a study of ancient life, and fossils are another important clue of Earth's history. Now we're going to talk about the formation and preservation of fossils. When we talk about preservation of fossils, these are quite rare, and the conditions that favor fossilization are rapid burial and hard parts. So when we do see fossilization, this is often during rapid burial. That's basically where sediment gets deposited right on top of the remains very quickly and basically prevents critters and other organisms from breaking and pulling that apart. Also, the presence of hard parts. So soft body material tends not to be preserved in the fossil record, but hard parts tend to be preserved more frequently. Also, death in an anoxic environment. Anoxic means without oxygen. that low oxygen environment or no oxygen environment tends to slow down decay. And so this can help preserve that fossil. Now, this is an image of a dinosaur fossil. The dinosaur dies and the soft body material starts to rot away. So just the bones remain. And then the water level rises and sediment buries the bones and footprints. Then we get a thick sequence of sediments accumulating over the bones, and gradually the bones fossilize. And then with time, erosion exposes that bed containing those bones and footprints. Okay. There are different kinds of fossils. There's frozen. These often happen in areas of permafrost or permanently frozen ground. You can also have dried bodies like what we see mummification that might preserve. You also have body fossils preserved in amber. That's a rare but complete preservation, or tar, where you have a very intact skeleton. There's preserved or replaced bones, teeth, or shells. These are often replaced by silica, but they can be replaced by things like pyrite. Molds and casts, which we'll get to in a minute, or carbonized impressions. This is where a thin carbon film is basically pressed out of that organism and leaves behind an impression, usually very dark or black impression on there. It's a very thin film. And then permineralized organisms, where basically it's replaced cell by cell. And petrified wood is a good example, or bone. And then trace fossils, these are the indirect fossil evidence. These could be things like burrows or tracks. So the first is frozen or dead dried body fossils. These happen in a few environments where you have whole bodies that may be preserved. This is a frozen body fossil. This is of a frozen mammoth. The soft body material has been preserved. Now you would want to keep this under an ice condition, and this could have a very horrible smell because it still could rot. And this is a preservation in tar. Whatever might eat it also got stuck in the tar. So these tend to be complete skeletons. Now, this is a bug in amber, kind of like Jurassic Park. Amber is rare but complete preservation, and this is from hardened resin of ancient trees that surrounded an organism. And in China, they actually found some dinosaur feathers trapped in amber. You can also have a replacement. This could be bones, teeth, or shells can be replaced. Some are replaced by silica, or some can even be replaced by things like pyrite. This is Archaeopteryx, which is a fossil mold. It is the predecessor of modern birds. You can see the impression of plume feathers on the wings and on the tail. Now, a mold is a cavity. It forms from weathering and dissolution, and the cast is basically the sediment that fills in that mold. Here's some ferns. These types of fossilization form from carbonization. This is where organic matter becomes a thin residue of carbon, and it leaves behind an impression of that organism. There is also called permineralization. Your permineralized organisms are where minerals are precipitated from groundwater that are seeped into pores or porous materials such as wood and bone. And it is a cell-by-cell replacement, so it preserves some of those tree rings. This is petrified wood. Petrified material is where cavities and pores are filled in with precipitated mineral matter, and that's from groundwater, and it's a cell-by-cell replacement, so those fine-grained details are preserved like those tree rings. There are also trace fossils. These are the indirect evidence of organisms. So these could be like your footprints, your burrows, and so on that are left behind by ancient organisms. These could also be indirect evidence like your coprolites. These are fossilized dung. You can find out if that particular animal was either a plant eater or herbivore, or if they had bone in their coprolites, you will know whether they were omnivore or carnivore. These are some footprints. These can give us some clues about the animal's gait, whether it walked on twos or fours. Now, when we look at different fossils, fossils have unique identifying features that help us identify them. We have trilobites here, gastropods, bivalves, brachiopods, bryozoans, crinoids, coral, ammonites, and graptolites. So for example, a trilobite has this 3-segmented body, a gastropod. Those are the same things that snails are. It has this kind of coiled shell, but it's not on the same plane. A clam or a bivalve, it has a symmetry across its hinge. A brachiopod has a symmetry across its shell. Crinoid might have a 5-fold symmetry. Your ammonite might have a coiled shell on the same plane. So there's different identifying features that can identify those particular organisms. Now, extinction was talked about by Cuvier, who lived between 1769 and 1832. Now, this idea of extinction is the idea that all individuals of a species have died. That's basically where organisms come into the rock record and then go extinct, so they don't reappear again. And this is based on the realization that not all fossil species can be found living on modern Earth. So this is a paleoartist reconstruction. So these are very different organisms than what we observe today. So there were different changes that we see throughout these fossil records. Now, this ties into the principle of fossil succession. This was developed by William Smith. He lived between 1769 and 1839. And this was a recognition of the distinct rock layers based on fossil assemblages. These are basically the rocks, the groups of fossils that occur within the rocks. And this principle of fossil succession basically states that ancient life succeed each other in a definite evolutionary pattern. And these fossils can help us determine the geologic ages of strata. So as we see these changes in the fossil, this is very powerful evidence that was able to help order these different rocks. These relative ages were based on the fossil assemblages, what rocks occurred. And that is because fossils change with time. There's an evolutionary pattern. There are organisms that are in the rock record that do not exist today. And so we could see that change happening throughout the geologic record. These organisms come into the rock record, they exist, and then they eventually go extinct. Okay, so we could see this happening in the fossil record. Now, another important thing relating to that is what is called an index fossil. This is very distinctive, abundant, widespread geographical distribution, and has a short range through time. The more narrow that this particular organism existed in time, the better it is to help constrain the time component when it came to the geologic strata. So this is basically illustrating that principle of fossil succession. These organisms existed for a span of time, then disappeared from the rock record, so they're no longer living on the Earth today. They went extinct. Now, where these fossils overlap, that can narrow down the ages. For example, down here we have some trilobites and what looks like some conodonts. And when we look at the trilobites and the conodonts, they have an overlapping range that they existed during, okay? Now, that constrains the time in which they could have existed because each of those have a different time and they could have only coexisted at the same during a narrower period of time. Over here, we have some more conodonts and then some brachiopods. And these brachiopods existed for a very long time, but they overlap with these ammonites here. Well, these ammonites have a very narrow restrictive time. So as they overlap, we know that if we see two different fossil assemblages or groups of fossils in the rock, those could have only occurred at a narrow period of time. So that's when we start constraining the ages, like these brachiopods and gastropods here. Where they overlap is the only time these two organisms could have existed together, okay? So that starts constraining where those fossil groups overlap. That is where that narrows down the age of those rocks. Now, quick question. How can the principle of fossil succession be used to determine the relative ages of the rock layers? These different species only existed for a period of time. And if you find two different species, two different organisms, they only have a specific period of time. So if you find both of them, they can only exist when they both overlap. And this brings us to our geologic column. Now, our geologic column is a composite stratigraphic column that symbolizes the entirety of Earth's history. Now, how was this constructed? This was using different spatial relationships among sedimentary rock types, the different principles, and also those fossils, those relative age principles when we talked about fossil succession. Okay, so you can't find all of geologic history at one outcrop. You have to explore the surrounding rocks to get a more complete history using correlation. And here's a chart of geologic time. And again, this was originally organized by fossil content and spatial relationships among sedimentary rock types. So relative age rules. Now, when we look at our different geologic times, there are different things that we're going to talk about. There's eons, there's eras, there's periods, and there's epochs, okay? So eon, era, period, and epoch, or epoch, either one's fine. All right. So eon is our greatest subdivision in time, okay? And so we'll start off with our eons. Now, here's our Hadean eon, and it's named for the Greek god of the underworld, Hades. And there's the Archean, the Proterozoic, and the Phanerozoic. Now, the Hadean, the Archean, and the Proterozoic make up the Precambrian. Now, the Precambrian it's an informal unit, okay? And it makes up 88% of Earth's history. Okay, so this geologic timescale is not to scale, okay? Because this represents down here 88% of Earth's history, okay? Now, when we talk about the era above that, this is called the Phanerozoic. And what the Phanerozoic means visible life. Okay, and that is made up of 3 different eras, okay? So the oldest one is the Paleozoic. That means old or ancient life. Then we have our Mesozoic, and meso means middle, so it's middle life, and you'll know that as the age of the dinosaurs. And then we have our Cenozoic, and that comes from recent. Okay, so it has the same root as recent. So that's recent life. okay? And we're living in the Cenozoic right now, okay? So our eon is our greatest subdivision of time. Then there's era, period, and epoch or epoch. Either one's fine. All right, so when we talk about geologic history next time, we'll focus on the Paleozoic, Mesozoic, and Cenozoic, but we will touch also on the Precambrian, which makes up 88% of the Earth's history. Now, you may hear different things like Paleozoic, like Cambrian, Ordovician, Silurian, Devonian, Carboniferous, like Mississippian and Pennsylvanian, and Permian. I won't ask you to memorize beyond this point. That's for a more advanced class. But basically, I need you to know the Paleozoic, Mesozoic, and Cenozoic, and the Phanerozoic, and the Precambrian on this chart. So for the Paleozoic, that we talked about that, the Mesozoic, that's the age of the dinosaurs. So that's the Triassic, Jurassic, and Cretaceous. And then for our Cenozoic or recent life, those are like your Paleogene, Neogene, and Quaternary. So I'm just going to ask you to memorize up to this point. You don't need to memorize this. This is for more advanced classes. We've been talking extensively about relative age dating, and now we are going to transition into numerical age dating or absolute age dating. This is where they use known rates of radioactive decay to date the crystallization of certain minerals. So this is isotopic dating or absolute age dating, where we would assign an age to the rock, like 113 million years old. Now, to talk about radioactivity, we need to go back to talking about the atom and talk about protons. Those are those positively charged particles in our atom's nucleus, neutrons, which are in the nucleus, which are neutral, and then our electrons, which are negatively charged, which surround the nucleus. Now, our atomic number is the number of protons in an atom's nucleus. And remember, that defines the element. And as we talked about before in our climate section, an isotope is an element that has the same atomic number and varying number of neutrons. So all elements are isotopes. Okay, there's just a varying number of neutrons. So they're the same element, just different number of neutrons. And there are stable isotopes, which we talked about before in our climate section. Those don't decay. And then there's our radioactive isotopes, and those do decay and break down. Now, again, our protons and our neutrons are in the atom's nucleus, and surrounding that is our electrons. Now, a great example to talk about when we talk about isotopes is carbon. Now, carbon has 6 protons, and that defines the element. So if it were to have more or less protons, it would no longer be carbon. Now, sometimes it has 6 neutrons, and the number of protons and the number of neutrons make up the atomic weight. And so when we talk about that, our carbon, which has 6 protons and 6 neutrons, is carbon 12. The next one may have 7 neutrons, and this is what we call carbon 13. And then the next one has 8, and that is called carbon 14. Now, carbon 12 and carbon 13 are stable isotopes, so those don't decay. But you probably are very familiar with carbon 14. Now, carbon 14 has a half-life just less than 6,000 years, and we'll define half-life in a minute, but that means that it's only useful for the last 80,000 years. So when we talk about carbon 14, this is not usually very useful for geologists because we're talking about deep time, but it is very useful for anthropologists because it can be helpful for more recent material. Now, when we talk about isotopic dating or radiometric dating, this is a technique for using the ratios of the radioactive elements to their decay products for calculating numerical ages. And we'll talk about half-life in a minute. And in geology, there is a specific field of study that focuses on isotopic dating using these radioactive isotopes called geochronology, chrono meaning time. And so this is a study of numerical ages of rock. So absolute age dates, those years, like what we say 113 million years old, that is obtained using geochronology. Now, when we talk about radioactive decay, this is the change of the unstable parent or radioactive isotope into the stable daughter isotope, okay? And a half-life is the time it takes for half of a group of atoms to decay, okay? So it goes from the radioactive parent to the stable daughter product. When igneous and metamorphic minerals crystallize, some of the elements within those minerals are radioactive, and they start off 100% radioactive. At the first half-life, 50% have already broken down into the stable daughter product. So that means that the remainder are 50% are radioactive. At the second half-life, again, 50% break down again. And so what we have is that we have only 25 remaining radioactive, and the 75% are the stable daughter product. So when we start off with 100% of the parent or the radioactive isotope and 0% of the stable daughter product. At the first half-life, 50% of the atoms have already broken down, and so we only have 50% that are radioactive, and the other 50% are now stable daughter products. On the second half-life, only 25% remain radioactive or parent, and the other 75% are now the stable daughter product. Now, different isotopes have different half-lives. So let's talk about first uranium-238, which decays to the stable daughter product lead-206. And that has a half-life of 4.5 billion years. And we see that there are uranium-bearing minerals in some minerals in rocks called zircons, and these occur in both igneous and metamorphic rock, and they're preserved because they're relatively very hard. They're also often found in sedimentary rocks from the pre-existing parent rocks. So these uranium-bearing minerals we're able to radiometrically date those and obtain an age of those rocks. We can also use uranium-235, which decays down to lead-207, and it has a half-life of 713 million years. Kind of a legacy radioactive element that they used to use a lot in geology was potassium argon dating. And this has a half-life of 1.3 billion years. And so they can date potassium-bearing minerals like mica, feldspars, and hornblends. These are often used for volcanic ashes to radiometrically date them. And when you obtain an isotopic date, what does an isotopic date really mean? It's talking about closure temperatures. So this is the temperature below which isotopes can no longer freely move in and out of a crystal. And so what type of rocks do you think can be radiometrically dated? Igneous and metamorphic rocks. If you were to do some radiometric dating on sedimentary rocks of those minerals that it contains, your date from those sedimentary rocks would be dating those inclusions, those chunks or fragments of older pre-existing igneous and metamorphic rocks. Now, how can we use our relative age rules and radioactivity and combine those together? those can be really helpful. All the same rules that we talked about before still apply. So we can still use those laws of superposition, original horizontality, the different types of unconformities, and look at those and compare one layer with respect to another, but also use our igneous and metamorphic rocks to constrain the ages of the sedimentary rocks. So for example, let's start at the bottom here. This is a granite and it's 125 million years old. So there's some different terminology we'll be using throughout the semester. GA stands for billions of years, and MA stands for millions of years. Okay. So this is 125 million years old. And what we know from granite and the type of environment it forms in, we know that granite is a coarse grained felsic rock, and coarse grained material, it cools very slowly. And so it took a long time for those large crystals to form. And we know that granite, like batholiths, they often form in the core of mountains. So we know that granite doesn't form at the Earth's surface. So there's a scour feature right here. This is called a nonconformity because there's igneous rocks below the erosion feature. And so this tells us that it had to be uplifted to the Earth's surface to be eroded and scoured like that. Okay, so there has to be some type of gap in the geologic record. Then we have a Cretaceous sandstone with fossil bones, and paleontologists for a very long time have been using those to apply those fossil succession rules. You can also look at invertebrates, marine invertebrates, to do the same thing. Then there's several other sandstone and other sedimentary layers deposited on top of that. And then there is this basalt dike that is cross-cutting these sedimentary layers and the granite. Now, the basalt dike has been radiometrically dated to 80 million years old. So we know that these sedimentary layers right here are anywhere between 125 million years to 80 million years old. So that's how you basically use those relative age rules to basically constrain the age of those sedimentary rocks. You constrain them by the bounding units. Now, at the top of this, we see a disconformity. Remember, those are the hardest to discover in the field, and then a nonconformity. And above that, we have a Paleocene sandstone and a volcanic ash that's 50 million years old. And so we are able to basically constrain the age of this sandstone between 80 and 50 million years old. Quick question. How can you obtain a numerical age for a sedimentary rock? First, you use those different relative age rules. What came first, second, third, put things in sequence, and then use your igneous or metamorphic rocks to constrain those units and basically radiometrically date those. Now, this is another image of our geologic time, and you'll notice that there's a lot more divisions in this one. Remember, we talked about the Precambrian last time. This one's a little bit more, not quite still to scale, but this one represents 88% of Earth's history. Now, when we look at this, this has obviously been altered because of those radiometric dates. Those basically, again, constrain the ages. And so you'll notice things like 4.540, 145 million years, 541 million years. Those are absolute age dates. So not only do we have our relative age rules, but we do also now have the constraints of those absolute age dates, those relative ages that were obtained by radioactive dating to define the time or the absolute age of these different rock units. Now, how old is the Earth? This is a question that people have been tackling for a long time. So Lord Kelvin You probably know him from kelvins, like temperature kelvins. In the 19th century, he calculated that the Earth was 20 million years old based on estimated cooling rates of the Earth. Now, Kelvin assumed that there was no new heat added to the Earth since initial formation, and he didn't account for two factors. He didn't account for convection, that cycling of heat within our mantle, and also radioactivity, okay? So he was not close to the age of the Earth. Now, when we talked about James Hutton, remember he's the father of modern geology. And when we talked about John Wesley Powell, when he explored the Grand Canyon and was mapping the Green and the Colorado rivers, he noticed that there was these very thick units. And when we apply those principles of erosion, those happen over very long time periods when we talk about our observations today. So when we look at that principle of uniformity or that uniformitarianism, that suggests a much older Earth. Now, when we do isotopic dating of our Earth-based materials, the oldest date that we get for our rocks on Earth is 4.4 billion years old, okay? So when we talk about our isotopic dates, why do you think we're close, but we're not quite there? So the Earth is 4.6 billion years old. Why do you think we're not quite to 4.6 billion years? Early Earth was molten. And we'll talk about it in our next lecture about the Hadean and how the early Earth was molten. Remember when we do radiometric dating or isotopic dating that we're dating closure temperature when those minerals crystallize in those igneous and metamorphic rocks. So if early Earth was molten, you would not be dating the rock until it had crystallized, okay? Now, how do we get that age 4.6 billion years when we're talking about the age of the Earth? That is from dating, isotopic dating of solar system materials, okay? So when we talk about it in our next lecture, it's basically believed that the solar system formed at roughly the same time. And so we date what are called meteorites, which are basically chunks of the early solar system that come to Earth, and we can radiometrically date them. They came from the formation of the solar system just like our Earth did. And those yield dates of 4.54 to 4.57 billion years. Now, quick question. Why have the assignments of numerical ages to periods on the geologic time scale changed? This gives you a hint right there. All right, thank you.